Hello, and once again, welcome to the second lecture on coordination compounds. Am I able to, or can you, guys?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. And in the Zoom, many guys have joined, including Mr. Patro, who and will join. And we have a lively class in some time. As I've told you, I'm now at San Diego, California State, US, and it is now 5. So in India, it is 5:02 in the morning, but here in the uh, in the west part of US, it is 4:32 afternoon. So I will say, I will address you. Good morning, guys. If you want to address me, good afternoon. So now, constantly at this time, I am being disturbed by my grandson, who is maybe 7 years old. He wants me to play at this time. He has already come back from school, but I won't go. So let me share my screen and start today's proceedings. We have discussed yesterday different types of ligands. I remind you, monodentate ligands are plentiful, large number of monodentate ligands. So also bidentate ligands having two teeth to bite. These are called dentic ligands, denticity. One atom will bite with a pair of electrons. We have seen ethylene diamine En, bipyridine B, bip, phenanthroline, propylene diamine, binap, DPP. These are not very important for the point of view of examination. Oxalato is important, 2 minus. Glycinato is important, 1 minus. Carbonato, ACAC is acetyl acetonato, PIAC benzoyl acetonato, dimethyl glyximato, often written as DMG only, but I used to write DMGH, is 1 minus. Sulfato, thiosulfato, and so on. Diethylene triamine belongs to the tridentate ligand category. We have tetradentate ligand, triethylene tetramine tri-En. We have pentadentate ligand. Most important is TEPA, tetraethylene pentamine. And we have hexadentate. This is very important. You can write down small letter 2, no problem. You can write small letter 2 or capital letter 2, 4 minus. If it uses all its teeth, then the coordination number is 6. But sometimes it doesn't like to use all the 6 teeth. although the charge is 4 minus, it is 6. And this is octadentate ligand. That was the last we discussed, octadentate ligand. Diethylene, triamine, pentacetato. Today we shall be starting here. There are some macrocyclic polydentate ligands. Let me open a blank page for today. You know, when supposing cobalt 3 plus is coordinated with ethylene diamine EN or any bidentate ligand or polydentate ligand, it forms a cyclic ring. And if there will be one more, there are two rings now. If there are two more, I mean one more, so this is CO En whole 3 plus. Because ethylene diamine is a neutral ligand, cobalt is in the plus 3 state. Same is the charge of the entire complex ion 3 plus. Now these two bonds are lying one above, one below, and these four are lying at the four corners of a square. So if you add, if you draw the line, the outline, you will find an octahedral figure will be coming up. So these are called chelates, cyclic complexes formed by polydentate ligand. If there is a tridentate ligand, then one ligand will form two rings. Bidentate ligand, one ligand will form one ring. And there are three ethylene diamine, it will form three rings, 5-membered rings each. So these complexes are called chelates. Therefore, the polydentate ligands starting from polydentate ligands are generally called chelating ligands. Because they form chelates. Chelates are nothing but cyclic complex. Cyclic complexes are called chelates, and that is formed by the coordination of at least a bidentate ligand. Any polydentate ligand will form one ring or more than one ring, and these complexes are called chelates, and therefore such ligands are called chelating ligands. Monodentate ligands are never called chelating ligands. Bidentate, tridentate, they are called chelating ligands. And one more term that I have already told you yesterday, that ambidentate ligands. They have two alternative donor atoms, but can bind with only one of them at a time. Hence, they act as monodentate ligands. Cn minus, if write Cn minus, it will mean carbon donor. If you write Nc minus, same formula, but just switch the two atoms, it will mean the nitrogen is the donor and the name will be isocyanide. And in the old naming system, it is isocyano. NO2 minus, if you write, we have written that. So these are called ambidentate ligands. OCN minus cyanato, NCO minus isocyanate. Hopefully, you have copied as much as possible. isocyanato. We also make tables. Till taught, I will be giving a file which is containing far more contents, which may not be completed in one class, but you write till taught from the main file. And I also told you what are flexidentate ligands. For example, sulfato, the denticity is 2, but it may or it may not use 2 teeth. If it will use 2 teeth, then it will be acting as a really bidentate ligand, but having 2 teeth, it will be using only 1 teeth. In that case, it's such a ligand having flexibility in using different number of donor atoms in different complexes are called flexidentate ligands. Here you see coordination number 7 is uncommon. So now, of course, the octahedral geometry can be verified experimentally by many other techniques. So these are octahedral complexes 4, and undoubtedly it is clear that sulfate now is using 2 of its heads teeth to bite. So 2 plus 4, 6. But here it is NH3 5SO4. Here sulfate is only using 1 tooth, keeping the other tooth intact without any use. So this sulfato is a flexidentate ligand. So also carbonato. The denticity is 2, but sometimes it will use 1 tooth. EDTA also is a flexidentate ligand. If you write EDTA, then it is using all its 6 teeth. And if you write HEDTA, its charge will be 3 minus. And chromium, now see chromium here is OH is -1, HEDTA is 3 minus. So the net charge is 1 minus x minus 1 minus 3 is equal to 1 minus. So x is equal to +3. So chromium is in the +3 state. Oxidation number, as we call the primary valency, +3, and coordination number is 6, because this is using 5 atoms, keeping 1 tooth without any use. 5 plus OH minus 1, 6. Similarly, in some other complex, palladium complex, only 4 teeth, and the charge will be -2. Other carboxylic acids are neutralized. Only 2 CO minus are there. They will, as well as the nitrogen donor, right? So palladium in the +2 state is a neutral complex. Coordination number is 4 here. So these are called flexidentate ligands. I would like to share the red book, and I will also keep that. I will share that file with you, the red book of directly from IUPAC. This is called the red book of IUPAC, where categorically from 2015 the change has happened. All the changes that this is chlorido. Chlorido you find here is chlorido, not chloro. Absolutely, there is no chlorobromoiodo or cyan. No, it is cyanido, chlorido. So this is the latest guideline directly from IUPAC source. So I will share this file wherever be challenged by anyone. You will be just throwing this file him or her to convince that the rule has changed. So you have to follow the new rules. But we will not hate the old rules of somebody writes chlorobromocyano. We will accept it. Old is gold. No problem at all. Now, We will talk more about the haptic ligands later. We will not discuss more about there is another type of ligands called haptic ligands, where one ligand will be using more than one atom. All the atoms continuously bind or link with the central atom. So if that is the case, it is called haptic ligand, and the number of contiguous atoms that coordinate is called the hapticity, not denticity. Denticity is a single atom. Ethylene diamine is a di or a bidentate ligand. There are two tooth, clear cut tooth, one here, the other one here. But if all the four atoms simultaneously coordinate with very typical bonds, the bonding is very complicated. We will be discussing that at the end. So those ligands are given a symbol eta. Eta and of atoms in that continuous series is written as a subscript, eta 5, eta 2. It is dihaptic, pentahaptic, tetrahaptic, trihaptic. For example, cyclopentadiene, which is aromatic, having 6 pi electrons, is a pentahaptic. Sometimes it can be monohaptic. It can be monohaptic. Only localized this one can also bond. Very, very interesting, complexes have been synthesized using the pentahaptic property of this cyclopentadienyl. In fact, it can also be called cyclopentadienido, not iodo, ido. Dine, E will be removed by ido. This is the latest. Dinyl is chalta hai. Cyclopentadienido. And cyclooctatetraene, which this is neither aromatic nor anti-aromatic. Although its symptom looking like anti-aromatic, it is non-aromatic because it's stop-like shape. But it can be octahaptic. All the 8 carbon atoms can be simultaneously be bonded with a very, very interesting kind of bonding that can be explained by molecular orbital theory later. Or some selected 1, 2, 5, 6, only 4 in the top. In the upper part of the top can be connected, so it will act as a tetrahaptic ligand. But the maxicity is 8. So ethene is a dihaptic ligand. Allyl carbanion is a trihaptic. You can also make it monohaptic, confining this lone pair to bond and the conjugated pi electron not to take part in the bonding. In that case, the haptic may be almost same as dentic. Benzene, all the 6 carbon atoms can be simultaneously coordinated with very peculiar bonds with the central metal atom. Dihydrogen, there is a sigma bond, but both the hydrogen can be coordinated by typical, bonding with the central atom. It's a dihaptic. Dioxygen is dihaptic. So, later on, you will find, I'm not asking you to write anything now, because this file I will be updating today. A lot of additions have been made compared to the file that I shared with you yesterday. You find a lot of other data. I did not include the haptic ligands, but since it is a complete file, I thought, why shall I talk about hapticity and haptic bonds, haptic ligands at a later stage? Why not now? And also you can classify ligands in three different ways that will be used later when we study metal ligand bonding. One is called sigma donor ligands, like ammonia, water having a lone pair, at least one lone pair to coordinate with the sigma bond. These are called sigma orbitals. Sigma orbitals that is present in a hybrid orbital that forms a sigma bond. So they are simple sigma donor ligands. The other one, very important ones in coordination compounds, is sigma donor and pi acceptor ligands. The ligand having a double bond or a triple bond like carbon monoxide, cyanide ion, nitrosyl, nitrite ion, where we have a lone pair on carbon here in carbon monoxide, carbon here, as well as a multiple pi bond, double bond or a triple bond. As a result, it will form a sigma bond by its donation to the central metal ion, which is the normal usual case of coordination, where the donor, the Lewis base is the ligand, and the acceptor, the metal ion, is the Lewis acid. That is the usual bond, sigma bond. But at the same time, these guys, they will form pi bond with metal ion. The metal ion will use the field d orbital to overlap in a sidewise manner to some of the vacant orbital of these ligands, anti-bonding orbital of these ligands, and that we is called a p pi d pi back bonding. If one of the p orbitals or d orbitals is vacant, the other p or d orbitals is filled, then that kind of pi bonding is called p pi or p pi d pi. It is in here, it is p pi d pi. D pi is the filled d orbital of the metal ion, and p pi is the empty anti-bonding orbital of the ligand. Talk about that later. Don't worry about it. So the third type is called only sigma donor and pi donor. No question of acceptor. A carbon monoxide, cyanide ion, they accept by pi mode, but these guys, they go for sigma bonding. They also go for pi bonding. They in both they act as donors. Guys like iodide, bromide, fluoride, sulfide, oxide, where these oxygen and halo accepting water, all other oxygen and ionic ligands. And of course, azide is very fragile, although nitrogen is there, but still it is under this category. It can form sigma bond by putting a sigma orbital and a p orbital for sidewise overlapping, both donation. And ironically, these ligands are called weak field ligands. We'll talk about what are weak field ligands. Although they are producing both pi and sigma, but they are weak field ligands, while these guys are heroes. CO, Cn minus, NO, NO2 minus, they're called strong field ligands. Just you remember what are strong field ligands. Just remember the term strong field ligands. We shall be utilizing them in our theories of metal ligand bonding. And these only sigma donors, neither acceptor nor pi donors, they are of intermediate strength. They are ligands having intermediate field strength. So with this, we will go for the nomenclature. We shall be writing now something. You guys make ready to go for a vigorous writing. Okay. We are, oh yes, welcome who are watching in the YouTube now or then later. So let me tell you that there will be a temporary break for a weekend here in US where I'm staying now. The weekend is celebrated with a lot of enthusiasm, excitement. Guys will not allow me to sit in my table, chair, to do anything. We have to go somewhere. Hangout, as we call in India, also, the hangout term is very popular. We hang out in different places and we enjoy the time. So that is why guys who are watching from a distance in YouTube, uh, if you then you should better subscribe to this channel so that immediately once I upload, I schedule any class, it will be immediately notified to you. It will be flashing in your timeline. So it is better that you subscribe to my channel if you are really benefiting from this program. So let us go for nomenclature. IUPAC nomenclature. First, let us talk about cationic.
societal एक बार और जो डिस्कस कर ले बॉन्डिंग के साइड.
Well, those things are for higher level things. I chose not to write Flexidentate ligands. You can write down at home. Krishna is asking that whether we should write now in our copies, in my presence here, about Flexidentate ligand, about,
No sir,
I
not
forgot to
about
tell you one thing. I forgot to tell you in macrocyclic ligands, yes, I skipped that. In macrocyclic ligands, it is one step more. They are polydentate but cyclic. The polydentate, bidentate, tridentate, tetradentate that we studied, they are all acyclic, open chain. But when it becomes a cyclic but polydentate, they are called macrocyclic. Macrocyclic ligands, they by definition, they contain at least 9 atoms, including the heteroatoms, more than 9 or more, and the denticity will be at least 3. Then only we regard it as macrocyclic ligand. Later on, we shall see how this ligand will have a profound effect in stabilizing the complex. That's called the macrocyclic effect. Talk about that later. So the crown ethers, the cyclic ethers containing multiple ether links are called ethers. The number of atoms in the entire ring is the first digit, first number. There are 12 atoms, including the 4 oxygen atoms. And this last number is the number of oxygen atoms. This is 12 crown 4 is this one. This is neutral, a tetradentate cyclic ligand. This is 18 crown 6. And most importantly, in biology, you guys know more than what I know about biology. So this porphine is the parent nucleus, porphine, and any substitution in different positions porphyrin. And the complex out of this porphine macrocyclic ligand is very, very important in biology. Hemoglobin, Heme, is the ferrous, is the central metal ion sitting at the center, and the different branches at different points. This is the porphin parent nucleus, parent structure. That is a non-entity. That is the porphin moiety part without any branch. But once it is branched in natural bio inorganic complexes, they're all branched, and branches are different in different complexes. This is a ferrous complex, Heme, with vinyl here, vinyl here, and CH2, CH2, COH here, CH2, CH2, COH here, methyl, here, here. So with ferrous, this is, and the chlorophyll is the same porphyrin primary structure with other branches, but magnesium is the central metal ion. So these are macrocyclic ligands, and here also we get multiple rings. These are also macro complexes, macrocyclic complexes, because the the ligands are themselves cyclic. So they will produce more cyclic rings while they will. So the effect, the stabilizing effect will be much more than the mere chelates that we found formed out of acyclic polydentate ligands. These are microcyclic complexes. And the ligands are called macrocyclic ligands. So these things we will prefer to write at home. And this is cyclam. And these are, I don't remember I told you or not, the secondary amine NH is called aja, not oja, aja. So this is tetra aja cyclotetradecane is called cyclam. The aja crown ether. O is replaced by NH. These are also macrocyclic ligands. And someone like Krishna or Priyabrat or Pulak, anyone watching uh, remote yesterday, a lot of chatting had happened when I discovered at the end a girl was chatting and answering my question. Maybe correctly. Today, I will make it a point to, because I have having two monitors, I will be looking at the charts of the YouTube as well. Along with you guys who have joined in Zoom, you can ask your question in Odia. I will translate to English, because whatever comes to your mind, language should not be a barrier between the teacher and taught for understanding purpose. So you write these things in details, leave some space to write about the macrocyclic polydentate ligands and chelating, some other terms like chelating ligands, because these are in fact monodentate ligands having two alternative donor atoms. Chelating, ambidentate ligands, chelating ligands. So these chelating ligands, they form cyclic rings. These are called chelates. Therefore, all polydentate ligands are called chelating ligands. Ambidentate ligands, cyano, isocyano, but I call cyanido, isocyanide. Flexidentate ligands having more teeth. You can use all teeth to bite, but you can also use less number of teeth to bite. Haptic ligands are very typical. Usually, an instructor avoids telling about haptic ligands in the beginning, but you guys are fantastic. I have no hesitation to introduce the difference between the dentic ligands having one teeth at a time to bite, but here in haptic ligands, multiple atoms, they bite together. Continuous atoms, they bite together, more than one, not one at a time. They have a good relation between them, and they use their sometimes bonding, anti-bonding. We'll talk about that later. The bonding is very, very interesting and also complicated for the beginner to understand, unless you learn the MOT, the molecular orbital theory of the ligand metal bonding. So this you write down at home. And also the classification of ligands on the basis of the donation and acceptance. Sigma donor only, sigma donor pi together, sigma donor and pi donor. These three kinds of ligands make the ligands, strong field ligands, weak field ligands, and ligands with intermediate fields. And now we shall talk about, am I clear, guys? I want to hear from you. Swastik, can you not write down at home these things so that we can save time, right? Swastik? Giriza?
Yes, sir.
Can you not write down Riddhi Siddhi?
Yes, sir.
Okay. Now, our most important part, before we start isomerism, which we will be doing today, we shall be taking up uh, nomenclature, cationic type of complex, where the complex is a cation. So the rule says first the metal ion, metal in English, as we call not herum but iron, not aurum but gold, gold in English, followed by oxidation state in Roman, IV, like that. In between parentheses, it is indicated here. I'm not writing in language. Nobody will ask you to describe how you name a complex. Oh, I'm so sorry. First is the ligands in alphabetical order. I'm so sorry. Ligands in alphabetical order. Ligands in alphabetical order, followed by metal ion in English, and immediately after, within parentheses, the oxidation state in Roman, followed by the counter anion with a space, one space, name of the anion. But there is no space in between, just like in organic nomenclature you found. Supposing I ask you to write down this. Now you have to tell me two things, oxidation state and coordination number, before you name. Of course, coordination number is not required for naming, but I will want you to tell me the coordination number. This is the amine ligand. Ammonia is called amine. Look to your copy. What is the name that we will use for the ligands while naming? This is aqua. What is this? What is En? Priya? Anyone watching from a remote place, sitting comfortably before the
Ethylene diamide.
what? Ethylene?
Diamine.
Ethylene diamine. Diamine.
It's not diamide, diamine. Carbon is there. If it is a metal H2, then we call sodium amide. In inorganic, when there is a metal nitrogen bond, the NH2 or NH becomes amide. The carbon nitrogen bond, NH2, is called amine. Okay. So this is a bident. What is the coordination number? First tell me. Yes, Sai?
2.
Sai? Coordination number.
6.
Precisely. Because these are monodentate ligands too. These are monodentate ligands too. And ethylene diamine is a bidentate ligand. One ligand has 2 teeth. So the total number of teeth that will bite is 6. That is the coordination number. And what is the charge? What is the oxidation state of cobalt? This is neutral, this is neutral, this is neutral. And the only charge that is staying outside is -3. So what is the oxidation state of cobalt?
+3.
+3. So then how you write? First, arrange all the ligands with the multiplying or multiplicative suffixes. If it is a simple ligand, then di, tri, tetra. If it is a complicated ligand, like it itself carries bi, tri, tetra, then for its multiplication, you know what multiplying prefix you use in organic, like tris, bis, tris, tetrakis, pentakis, and so on. So, unfortunately, you know, here you are advised to put a bracket. Every ligand you put a bracket. Only the monoatomic ligand like Cl, Br, oxido, chlorido, bromido, you may not, IUPAC is saying you may not put any square bracket, I mean parenthesis, to group the ligand. But in all other polyatomic ligands, you have to put a parenthesis and the subscript, the number of such ligands to be written as a subscript after the parenthesis. Now, therefore, I put a parenthesis. So, which is first? Aquaramine, AMMNOQ. So, tell me who can tell me the name? Anyone? Raise your hands. Tell me the name. You can write down, guys. Those who are watching in the YouTube, tell me the name. First, arrange these aqua. This is amine, double M, amine. This is aqua. This is ethylene diamine. No gap. This is single M. And this is di. This is di. If it had been 2, then it would have been bis. Because ethylene diamine contains di. Therefore, it becomes a complicated ligand. We can't call complex ligand as we were telling in organic, because the coordination compounds are funnily called complex compounds. From time immemorial, so we will not use the term complex for the ligand type. Yes, tell me. The di, tri, tetra, bis, they are not considered for alphabetical ordering that you know from organic. Yes, Udit.
Diamino, diaqua,
Not
ethylene
amino. Are
diamine,
you kidding me? Di? What? Is it amino or amine? Udit,
sorry, sir. I mean,
what? Tell me again. People will hear you.
uh,
Tell me again.
diamine,
Diamine. Yes, not amino.
diamine,
Then
diamine, diaqua, ethylene diamine,
diaqua.
cobalt,
Then
ethylene
ethylene
diamine, cobalt
diamine.
5 chloride.
Yeah. Slowly. Ethylene diamine. We have
Cobalt 5,
compared A,
cobalt
AM.
3,
This is AQ. This is E. Di, tri, tetra, they are not considered. So diamine, diaqua, ethylene diamine, all the ligands are over. Then the metal.
cobalt
I don't
3,
have a space here. I'm writing below cobalt, and within parenthesis is oxidation state in Roman. What is the oxidation state we have determined? 3.
triple I.
Plus 3.
Yes, sir.
I. Don't write plus 3 in Roman. I. Then chloride.
Yeah.
Then chloride. Not, you don't write it's a simple ligand. Sorry, simple ion. So write chloride. Simply chloride. It's because it is plus 3. So it has the net charge of the complex ion is 3 plus. Therefore, there will be 3 chloride ions to balance the charge. Simply chloride. Not chlorido. That is not a ligand. Had it been a ligand, chlorido, or I don't mind if you write chloro. But we are, the quality of guys we are. Okay. I will give you another one. Well, you have to tell me oxidation state and coordination number first before we move forward. Yes, guys. I didn't understand. Please
Plus
explain again.
oxidation state
In
plus
excess,
3.
tell me which part you did not understand. In excess India, please tell me. You just follow me in excess India. I am explaining once again with this new molecule where I have deliberately taken to be a positive ion. The complex ion is positive, having +1 charge. Therefore, bromide is -1. Because bromide, you know, has a -1 charge. Therefore, the entire complex will have a +1 charge. So find out the oxidation state of chromium. Yes, Krishna?
Plus 3.
And what is the coordination number?
6.
Yes, you are looking not confident. Yes, anyone? Sai?
Yes, sir,
What is
6.
the 6? Because ethylene diamine is a bidentate ligand and there are 2 ethylene diamine. So 2 plus 2, 4 will be 4/10 will be supplied by 2 ethylene diamine and 1 nitrito O 1 plus cyanide 1. But since nitrite is a anionic ligand with -1 charge, we don't write here, but we know cyanide is a anionic ligand with -1 charge. Ethylene diamine is a neutral ligand. So to find out the oxidation state of chromium, let's say it is X in excess. Let's say it is yes, correct. In excess has answered very correctly. Thanks, in excess India. Supposing cobalt is X, this is 0 and this is -1 and this is also -1 and the net charge is +1. Let us forget about this bromide. Look, we have already identified the net charge of the complex. It's +1. So what is X? It is X is +3. So in this way, you have found out the oxidation state of the metal ion and the coordination number. Then who can name it? Write down the name in excess India. You have to arrange the ligands in alphabetic order because cationic, whether it is cationic or anionic, first before the metal ion you have to write all the ligands in alphabetic order with their appropriate prefixes like di, tri, tetra or bis, tris, tetrakis. When you write bis, tris, you have to put again a parenthesis to write the complicated ligand. I will not say complex ligand, complicated ligand, difficult ligand, which contains itself di. Yes, raise your hands who can answer. Amlan?
Sir, ONR nakun.
Yeah, Krishna?
Sir, ONR nakun.
It seems that you have not written a table. You look to your table. What is ONO and what is NO2? They are ambidentate ligands. If you write NO2, it has got a name, different name. If you write ONO, although the formula is same, contains 1 nitrogen and 2 oxygen and charge is -1, but it is the donor atom is oxygen here. So the name is different. Who can tell me the name? You have to write down. You can't say that I don't write anything at home. In Excess India, why did you delete all the charts? This gives me, I'm sad. I'm really sad. Not nitrogen dioxide. Not. Yes. Yes, Riddhi and Siddhi.
Cyanido, diethylene, diamine,
No. I am asking what is the name of this ONO -1 ligand? Yes, once again, please. Once again, please.
nitrito.
not simply nitrito is not hero marka answer. We have to be little hero marka. I mean, I used to say that you have to be modern, updated, recent in your naming. What is it? Simply nitrito or nitrito O?
Nitrito.
Nitrito.
Yes, Sai is correct. Now see, the file I have given you all the, this is nitrito, nitrito N. It is NO2 minus. Nitrogen is the donor. And if it is oxygen donor is ONO minus nitrito O. Previously, it was called simply nitrito, and this was called nitro. I have given both. Coming to today's program, we will have, let us write down first. This is nitrito N. This is cyanido or cyano C. This is ethylene diamine. This is not considered. E. So which will be written first? C. So tell me, anyone who can tell me, not nitro, in excess India it is nitrito O or simply nitrito, because had it been NO2, first N, then nitro. If it is ONO, it is nitrito O or simply nitrito if you are of the prehistoric days. You can also write nitrito. I honor. History is also a good subject. People say, what history, guys? They only study what has been happened already in the past. So we learn, we take lessons from the past mistakes and also do good things as our predecessors have. So learning of history, as studying the characters of our forefathers of these years is important. Now tell me how you write down. Yes? Anyone?
Cyanido, base ethylene diamine,
Cyanido.
nitrito,
First comes, it is
base
only one. Then ethylene.
base
There are
ethylene,
base in between parentheses. Ethylene diamine. Ethylene diamine, single M. Then nitrito O or simply nitrito. All the ligands are full. Then coming to
chromium
the
3
line.
bromide,
What? Chromium?
3 bromide,
Chromium III. Then the counter ion bromide. So this is the way you have to name a catalyst. And the neutral complex has no anion. Counter ion is, there is no anion, there is no conductivity. So the procedure, the rule, same as cationic complex. There is no anion. You will just leave it there. And NO2 whole 3. My net connection is sometimes becoming a little wild, going weird. So please bear with me. And some part, if you cannot watch, you rewatch it later by opening the YouTube recording. So now you have to tell me the same two things: coordination number and oxidation state.
oxidation state +3, coordination number 6.
Because ammonia is zero charge, I mean, this is nitrito N or simply nitro as previously called. It is -1 and there are 3. So total negative charge is 3. So cobalt has to be in state. So This is plus 3. Coordination number is 3 plus 3. There is no bidentate or tridentate ligand. This is 6. So coordination number is not important for naming. And well, how to name? Who can name?
Triamine nitrito O cobalt.
Oh, are you kidding me? How can it be nitrite O? When you write ONO, it is nitrite O. When you write NO2, it is nitrite N. Understand, Pulak? Krishna? So it will
Yes, sir.
be what? It will be
Yes, sir. Yes,
tri,
sir. Triamine nitrito N.
amine, triamine, amine, amine, triamine, then
Nitrito N
Hari.
cobalt 3.
Oh, are you kidding me? What is tri? Triamine
Yes, sir.
and
Trinitro.
trinitrito N, or you can
Cobalt
write
3.
simply trinitro, as was the case earlier. People are writing. Even in the book, you find NO2 is for nitro. But I will tell both. Write the latest rule. So triamine, this A is considered for alphabetic ordering. This N is considered the tri, and tri are not considered for alphabetical ordering. So triamine, trinitrite N, then comes cobalt. Cobalt, how much?
3.
3.
1, 1,
That's
1.
it. Oh, I, or 3. That's it. No anion is there. So it is similar to the cationic complex. So you try to write another one. Say you have chromium En whole 3. No. Oh, I would want to make it 2 and Cl2. Make it neutral. I would like to make it neutral. No ion will be floating to the left or right. Make it completely neutral. So quickly tell me the name. Yes, in XII India today, don't please, in XII India, don't delete the messages. You are writing correctly. So one mistake you did, it is that was ONO was nitrito or nitrito, and NO2 is nitrito N or nitro. Otherwise, you are doing fantastic. Now tell me, what is the name, Krishna?
Dichlorido. Diethylenamine.
Dichlorido or dichloro. Most of the books you find in the market will be writing dichloro. Then
Diethylenamine.
no.
Bisethylenamine.
Amlan?
Bisethylenamine.
Yes, base in between bracket what? What is En?
Ethylenamine.
Not ethylenamine. Are you kidding me? Amlan, what is this? Amlan, are you sleeping?
Sorry. Ethylene diamine.
Diamine.
You are sleeping. It's early morning time. So, yes, in excess you can call it ethane 1,2-diamine. And the IUPAC name is no doubt ethane 1,2-diamine. But complexes ethylene diamine has been accepted by USC as the name. It's so popular that instead of writing ethane 1,2-diamine, ethylene diamine has been accepted. Dichlorido, bis-ethylene diamine, then chromium, how much? What is the oxidation number of
2
chromium now in this case? In
plus
excess
2
India?
plus 2.
2, because this is neutral ligand and this is, there are 2 chloride ions inside the coordination sphere. So -2, so this will be +2. So chromium II, you know, they can exhibit variable oxidation state. You know, this transition metal ions are very, very prompt in forming complexes easily with large number of oxidation states. Now coming to C, anionic complex, the rules are different. First, the cation, but because that is the counter ion, the spectator, followed by the ligands in alphabetic order, the same way you did for cationic and neutral complexes, ligands in alphabetical order. Followed by the name of the metal in Latin. In this case, you have to write Latin, ferrum. Of course, the suffix ate. Then, in between bracket, the OS in Roman, the and IUM. Only if at all you find in the name of the Latin name, the last two letters or three letters are respectively and ium are replaced by the suffix ate, like ferrum. This is the Latin one. Chromium, the IUM is chromium, the IUM is replaced, and it becomes a funny chromate. People can confuse with CrO for 2 minus, but no, it is only one chromium. This is chromate. But if there is no and ium, like cobalt, then it is cobaltate. No replacement. 8 will be definitely there. If it is nickel, it is nickelate. No replacement. But the exception is, if it is mercury, you don't use hydride, mercurate, exception. RY is by 80, mercurate, not hydrazirate. Hydrazirate is the Latin word, but mercury, the IUPAC is exceptionally using mercurate, not. Now, let us first find this one. One. Where the complex is an anion. The complex is an anion. In the first case, we took the complex as cation, the second category complex as neutral, and now complex is anion. NXS India is repeatedly deleting the message. Why you are deleting is taking so much of strain, Baba? Okay. Yes, let me tell you first one together. First, you have to write
potassium tetracyanide,
then a space,
cuprate.
one space. Then tetracyanide. There are 4 tetracyanide. And this will be cuprate. And what is the oxidation state? This is -4, this is +3. This is very important. If you miss out the correct oxidation state, then you are lost. If it is an MCQ, you are lost. So what is the oxidation state? Yes, Amla? +1. Because potassium, there are 3 potassium +3, and there are 4 cyanide ion -4. So supposing this is X. So +3 plus X -4 is equal to 0. X is equal to +1. Or if you take the complex at charge 3 minus, because there are 3 potassium So the complex will have a net charge of 3 minus. You can have x minus 4 is equal to minus 3. So x is equal to plus 1. So this is potassium tetracyanide So similarly, you can do this silver complex, which is very, very important in metallurgy, that we shall study in metallurgy. This silver complex, which is an anionic complex.
cuprate 1 लिख लें.
Cuprate 1, I missed out. Cuprate, yes, cuprate I. The oxidation state should come as a, in Roman, in between parentheses after the name of the metal, in Latin with the suffix ate for ium, and if there is no ium and simply ate. So what is the name of this compound?
Potassium dicyanide.
Potassium,
Dicyanide.
then dicyanide,
Argentate.
argentate, yes, because
1.
argentum is the Latin word. So is replaced by it, argentate. That is not all. You have to put the oxidation state.
1.
Because there are 2 cyanide ions, the total negative charge is -2, potassium is +1, so silver has to be 1. Silver usually has +1 state. The +3 state is a very, very difficult. It's highly oxidizing. So it is I. Similarly, if it is Au, it will be orate. Okay, let me or you could have given OX. I could have given OX also. That means oxalato. I am not putting these ligands in proper order. The, the, the actual way of writing the ligands after the central metal ion is the same alphabetical order that you write the name. But the only difference that people do not do is to show the ligating atom, the donor atom. For example, water should be written as OH2. Ammonia is okay, nitrogen is the ligating or donor atom, so an ammonia is okay. So also nitro is okay, and ONO is okay. Similarly, water should be written as OH2, but we always make this mistake again and again. We write H2O, but the IUPAC says that you bring the donor atom first. And arrange all the ligands while writing the formula from the name in the same manner as you write the name, alphabetical order. There was earlier, the rule was to write the negative ligands first alphabetically, then the neutral ligands, then the positive ligands, if any. We have not yet taken any example having positive ligands, I mean positive ions, like NO+. We'll be doing that later. So there is a controversy about the writing of formula from the name. Some people stick to the old rules, write the new rule, but we will go for the new rule. People are not at all serious or very critical about whether you write first or second interchange. They are not, but about naming, they are critical. While I construct the formula of my own, I am not giving any attention in the proper ordering of ligands in the formula. So it will be this. Now you have to write down the name as well as it is now 6:10. we'll be taking another 5 minutes, and I'll tell you what to do at home before we reunite on Monday. I mean, sorry, your Tuesday morning. I will be scheduling much before the class, so you will be knowing, and those who are watching our website, theuranium.in, www.theuranium.in, they can get also the information there, and those who have subscribed will get the notification, and you guys who are with the Zoom, you can get my message when it will be scheduled. I will be giving you a lot of homework which you should come prepared and ask your doubts. Yes, in excess, India is correct. Potassium, that one, this one, tetra, cyano. You know this in excess India, you have to be little hero marka. We have been time and again saying nowadays it is cyanido. When you are with this, although looking like an old man, is not old really by heart. 16 years old is my heart. So I am giving you the modern name cyanido in excess India. Tell your friends it is cyanido. You are writing old things. Okay, we don't mind old, but the new name is cyanido. Okay, and what is the name? Yes, Krishna.
Potassium cyanide, trihydroxide,
Be
oxalato.
slow. You are very fast. Here in
Potassium
US they
cyanide,
call fast. Fast.
cyanide,
This is oxalato, and it is 2 minus. This is cyanido, C, 1 minus. This is hydroxido. They were calling hydroxo. uh, hydroxido, minus 1. So this is minus 3. This is minus 2. Oxalato dentate ligand is minus 2. Only one cyanide minus 1. And this is X. This is plus 3. So plus 3 plus X minus 3 minus 2 minus 1 is equal to 0. So X is equal to plus 3. So chromium is in the plus 3 state. This takes you back to class 10, class 9, how to find the oxidation number. Therefore, I categorically told you, you must recognize which ligand of how much charge, whether it is a neutral ligand or an anionic ligand. Usually, cationic ligands are very, very rare. Tell you some rare, you will find cationic ligands. So, oxalato is a bidentate ligand, minus 2. This is minus 1. There are 3 hydroxido. So, how to write? Give me the name.
potassium cyanide,
Cyanido. This C comes first. Cyanido. Then
trihydroxide,
trihydroxido or hydroxo.
oxalato,
I am not at all critical about the
oxalato,
old. This you can write cyano. Then oxalato. Then
chromate
what?
6,
Chromate. Chromate 3. I.
so 6, 3.
Are you kidding me? We found out the oxidation state is plus 3. So it has to be 3. Not coordination number you have to write here. You have to write the charge in Roman. I. The oxidation state. Got it? Got it?
Yes, sir.
Now, here is a post for so many update the file. Those who are downloading the file from the YouTube description box, I will also upload the file. You will find here there are so many. You just have a look. I will take another 5 minutes. This we have already done. And in every type, there are cationic. This example I have not given in this discussion. I have given some other. You write of your own, find the oxidation number, and coordination number, and write the name I have written, and some other I have asked you to find out. You write of your own. These I have written the name. This is tris. This is a cationic complex with 3 ethylene diamine. So tris ethylene diamine and chromium 2 nitrate. So you practice neutral complex. You practice those which you have not done in our program. You do it from this file. Even if some names are already given, you don't look to my name, you write of your own. And any complex. See, one which we have been telling, potassium percyanide. Tell me what will be its IUPAC recommended name. It is potassium cyanido, or you can call hexacyanoferrate 2. Similarly, the sodium, you write down, you already know glycinato, oxalato, carbonyl. This is carbonato, which is a bident. You have to see. Rarely the coordination number exceeds 6. So when I have asked you coordination number, whether you take carbonato as a real two-teethed or one-toothed, you have to find oxalato is always bidentate. And glycinato is always bidentate. Although it is -1, oxalato is -2, but bidentate. 2 plus 2, 4 plus 1, 5. So carbonato must be using one tooth. Although the charge is -2, for calculating the oxidation state of cobalt, you have to take 2 minus the charge. But coordination number rarely goes up, so it's still 6. Carbonato I've introduced is a flexidentate ligand. Can use 2, also can use 1. Most of the time it is 1, because if it is using tooth, not teeth, 2 tooth, then it will form a 4-membered ring, which is very, very unstable. Therefore, most of the time, carbonato, sulfato, they use 1 tooth. Of course, sulfato using 2 teeth, carbonato using 2 teeth are also there. They are uncommon, less common. So you write all this potassium, and this is lithium tetrahydrido, not hydro, tetrahydrido aluminate, as if you are giving AlO2 minus, AlO3 3 minus. This is looking like funny, aluminate. And I will next time talk about 18 electron rule. We'll not discuss, it will take a long time, not long time, 5 minutes. And I will tell you some examples of ligands having hapticity, dihaptic ligands, and have introduced here. I will not explain another pentahaptic ligand, cyclopentadienido, dinyl with iron, the sandwich complex, iron in the middle, and 2 cyclo, therefore bis cyclopentadienido at the top and bottom with opposite conformation. We'll talk about that later. And here is cyclooctatetraene, which is, although octahaptic, but it has used only 4, 1, 2, 5, 6. These 4 carbon atoms are used. Therefore, the subscript 8 or 4 is not done. You have to mention which carbon atoms are being simultaneously coordinated to the central metal ion cobalt. Forget about them now. Forget about 18 electron rule. And I will also tell some complexes having bridging ligands. These are called binuclear complexes, where there is one metal ion. Called binuclear. Don't be, swayed away by the term nuclei. Nuclei is a complex. There are 2 central metal atoms. This is called binuclear. If there are 3, then it's trinuclear. And in general, they are called polynuclear, where the bridging ligands are given the prefix mu. We'll talk about that later. Mu. And we could not do it because I found that you are really a beginner and you are going slow. But what you do is the exercise. The one which have been already done in my program, in my file, which we have not done in the class today. You have to, and this exercise, the following complexes, you have to name them, write the formula from the complex. You have to do the opposite. I told you how to do that. Same, because somewhere I have written here, writing formula from the name. The name of the metal is written first, followed by the ligands in the same alphabetical order as written in the name. But the ligating atom or the donor atom has to be shown first. Bridging ligand should be given a mu symbol before that. And they should be shown in between the two metal ions. We'll talk about that. Bridging ligands, you don't answer the question. I will tell you. Monoatomic ligands may not be given a parenthesis, but polyatomic ligands should be put inside a parenthesis. So you do this, do this, do this, do this, so many, do this. Here only ions, molecules are given together. So if you are given asked to find the, write the formula of the ion whose name is given, or the formula, or the name from the formula of the ion given, you can do that. You can also do all this. So accepting, I have not given any example having haptic ligands here. I have reserved for a future program, and but I have introduced what is haptic ligands, what is hapticity, but some examples I will give you in the next class. And but you have to complete this first, the given ones, then the exercise. And if you find in the NCERT book or any resource, you also practice, because we have 3 days before resume the next class, or 4 days you can count. So must be ready. So we are now closing our program, and those who have watched in the video, in the YouTube video, so Sivang Tiwari is writing Guruji. I think Guruji word is from the culture of the uh, Saraswati Sishu Mandir. Yes, Sagird ji, Sivang Tiwari is writing, and Sivang Tiwari is not a student. मैं स्टूडेंट नहीं हूँ, कोई बात नहीं, आप टीचर भी हो सकते हो. अगर मेरा कोई गलती हो जाता है, आप पॉइंट आउट कर सकते हो, क्योंकि क्योंकि टू अ human being is liable or gullible committing errors, and it is the human beings who find the errors. Okay, so with this note, I today's session. First, signing out from the YouTube watching guys, you can call it watchers, viewers, and then see you after a quite a long time. I'll take 3 to 4 days, but if you have not subscribed, please, that you get the notification sooner I schedule the meeting. So we'll meet in the next class. Bye bye. Bye bye.
Sir,
And
तारा
you
answer अच्छे.
guys, yes, Hamdan, RS, and Krishna. Anything?